Hi, welcome to our next lecture on pre-calculus. We are going to start logarithms today. We mentioned it last time, but today we are going to go through the basic properties. So I explain properties of logarithm which will help you to answer this type of questions quickly. So let's go ahead and see what is our setup in this problem. So we have our main definition, which is if you have an exponential expression b raised to power of a is equal to some number c, then you can write this as logarithm of c in base b is equal to a. And also, if you start with this expression, you can write it in the exponential format, which is here. So this is called the exponential form, and this is called the logarithmic form. You notice there is a little bit of asymmetry here. Here we are mentioning the name of the activity logarithm, but here just an arrangement of the letters that implies exponentiation. Sometimes in some computer programs you see they actually use the exp for exponentiation. Sometimes they use the word POW for power and such, so that we actually naming what we are doing. But the standard format is to use this type of arrangement of letters to indicate what we are after. Okay, first let's go ahead and just practice. So I'm going to be writing some examples to make sure we are all on the same page. So if you have 5 squared is equal to 25, another way of saying the same thing is to say that logarithm of 25 in base 5 is 2. Here's another example. You're familiar that 10 cube is 1000. So what if I want to extract that 3? I will say logarithm of 1000 in base 10 is 3. So logarithm is a way of extracting the exponent. So 125 to power of a third is 5. Another way of saying this thing is that logarithm of 5 in base 125 is 1/3. Let's give a negative example as well. 2 to the power of minus 3 is 8. Another way of saying this thing is logarithm of 2 to the power of minus 3, of course, is 1/8. Logarithm of 1/8 in base 2 is minus 3. Okay, so that must be enough examples to explain what do we mean by these two forms. Sometimes some problem says convert to exponential form, sometimes they say convert to logarithmic form. That's what's meant by it. Next, main properties. So when logarithm was invented, it was hailed essentially the same way computers are hailed today. Computers simplify our life. Logarithm also, when it was introduced, it was thought about in the same way. Let's see why is that. Logarithm of a product is equal to the sum of the logarithm of the entries of the product. Now, why is this important? If you have practiced multiplication in elementary school, you notice it's kind of a laborious exercise. If you have two 5-digit numbers and you want to multiply, it takes quite a few minutes. But addition is a lot simpler. So that was the main advantage of logarithm. Here you have multiplication, so this multiplication is being converted to this addition here. You have to be very clear about what's going on in these cases. Let me write an example. If you have, for example, logarithm of, say, 4 in base 2, and to that you add logarithm of 8 in base 2, what you get is same as the logarithm of 4 times 8 in base 2, which is logarithm of course, 32 in base 2. Easy to check. This is 2, this is 3. These are the exponents. 2 squared is 4, 2 cubed is 8. When you multiply them, you get 2 to the power of 5. So what this rule of logarithm says is the reverse of something you had in your algebra 1. If you have b to power of m times b to power of n and you want to multiply them, you add the two exponents. Now since the logarithm extracts the exponents, when you are taking logarithm of this product, you are extracting the exponent, which is the sum of the individual exponents you had. Okay, similarly, you had logarithm of m over n in base b. That is logarithm of m in base b minus logarithm of n in base b. Again, if you remember from middle school, dividing two numbers used to be quite a bit of hassle. What we are doing is that we are simplifying this fraction to the level of subtraction. Subtraction is a lot easier than fraction. Next, well, let's give an example for this one as well. If I have logarithm of, say, 64 in base 2, which is 6, and I subtract from that logarithm of 16 in base 2, which is 4, what I get is the same as logarithm of the ratio 64 over 16 in base 2. In both cases, this is 4, in base 2 is 2, and of course this is 6 and this is 4, and 6 minus 4 is 2. So what this rule saying is, again, sister rule of something you had in your first algebra class. If you are taking the ratio of two exponential numbers, you subtract the two exponents, and this subtraction here is the same as this subtraction over there. Third rule that we have is the logarithm of an exponential in base b, same as the exponent times the logarithm of the base of that exponential expression in same base. So for example, logarithm of 25 cubed in base 5 is 3 times the logarithm of 25 in base 5. Both of them, of course, are simplifying to 6. Now, these are the main properties. So this is the main property here. Again, notice that the exponentiation here is simplified to the level of multiplication here. So each activity is simplified one notch. Multiplication to addition, division to subtraction, exponentiation to multiplication. Okay, one thing I forgot to mention from at the outset, in the definition of a logarithm, the base b is always positive and also is taken to be a number other than 1. If we violate that, all sorts of things are going to break down someplace. So b is always positive and larger than different from 1. Typically it's a number actually larger than 1, but it could be between 0 and 1 as well. Okay, we have special rules. So we have some special case when the number that is involved is just 1. You remember b to power of 0 is 1 from your pre-algebra. That tells you logarithm of 1 in any base b is 0, which implies the following. If you have logarithm of a unit fraction 1 over n, here I had m over n, but what if it is 1 over n in any base? Well, it's going to be logarithm of numerator minus logarithm of denominator, and this is just 0, and we end up with minus logarithm of denominator. So we have this case for 1. Something that we are going to practice later on, but I'm going to mention among the rules of logarithm now, and then postpone the exercises to a future lecture. A so-called change of base formula. Change of base. What does that mean? Sometimes a problem asks you to calculate logarithm of some number in some base n. Of course, your calculator has several logarithm buttons. One of them is logarithm in base 10. Sometimes this is written as capital LOG, but in advanced books this notation is reserved for something else. And then there is logarithm based in special number e, which we are going to talk about later on. E is a number as famous as pi. Approximate value of it 2.71828, etc. That on your calculator has a special notation of little l, little n, lowercase ln, sometimes referred to as natural logarithm. So these are what is available on calculator. So if somebody wants logarithm in base 3 or 7 or 17 and such, it's rare, but what if you want it? Here's how to do it. Change of base formula. This is logarithm of m in whatever base is available to you divided by logarithm of what was the base here. Now in the common base b, so b can be 10, can be e, could be actually anything. So this is called change of base formula. Sometimes written in the other way. If you cross multiply, you get logarithm of m in base n times logarithm of n in base b is same as the logarithm of m in base b. So if I cross multiply this thing, I get that. As an example, suppose you want to have logarithm of 7 in base 3. When no calculator bothers to put a button separately for logarithm in base 3, what you do is take a logarithm of 7 in base 10, divide by logarithm of 3 in base 10, and then you'll be all done. It's also same as taking the other logarithm that's available to you, the natural log, and if there was any other logarithm available on your calculator, you could have done that as well. Sometimes in computer science they have logarithm base 2 to be special and available and so on. You could have used that one as well. Okay, these are the basic properties of logarithm. The last one, change of base, we might come back to this later on, but now it's going to be easy for you. This is this is the ratio rule. So on the right hand side you have 11 over 8. Well, this is the multiplication. What times 5 will be 20, of course, same as 20 divided by 5, and that's going to be what? That's going to be 4. 27 in base 5. Well, 27 can be written as 3 cubed, and here we had the property that the exponent comes in front and the base goes there. So the number that is required here is 3, because 3 cubed will be 27. Okay, so you want to practice the rules of logarithm and understand the reason behind them, because we are going to be working with them quite frequently. One more thing let me mention again here, which is just rewriting the properties of logarithm, sometimes in the context of identities. B raised to the power of logarithm of m in base b is just the number m again. What does this mean? It means exponentiation, and this logarithm, so we have one exponentiation and we have a logarithm. These two cancel each other and you go back to the number you had started. For example, let's make it clear, like 3 to the power of logarithm of 9 in base 3. Well, logarithm of 9 in base 3 is 2, because 3 squared is 9. And here you are being asked what is 3 to that 2. Of course it's going to be 9 again. But we don't need to calculate any of the intermediate steps. This number b raised to the power of logarithm of any number in the same base is going to be the number that we started with. We're just going to go back to whatever we had. So even if you had some unfriendly looking number here, like say pi to the power of logarithm of radical 2 in base 5, this looks like a scary thing, but it's just all red herring. Output is just square root of 2. If you apply a function to its own inverse function, you go back to where you had started with. Another way of writing the same idea is that the logarithm of an exponential expression in the base of that exponential expression is just the exponent. Again, that looks kind of cryptic as to what's being said here, but let's write an example. You will see immediately. If I have logarithm of 3 squared in base 3, I'm asking 3 should be raised to what number, so that it would be 3 raised to the power of 2. Of course the answer is just 2. Again, we don't need to know the intermediate steps. Always the answer is the number you had started with here. So these two identities come in play in some problems, especially later on in calculus. We are going to make use of them, so we might as well have them in front of our view now. So we have some identities here. We have the change of base formulas. We had a special case for the number 1. And we had the basic rules of the main properties that you see at the core of the simplest problem that we have in this section. Okay, very good. So until next time, good luck and God bless.